Okay, hi everyone. My name is Tomislav Smolčić. I work in Srce, University of Zagreb, University Computing Center. And today I will talk about what's behind this long title is implementing new GPUs NVIDIA Tesla V100 into our computer cluster at Srce, Isabella. So short definition, what is actually high performance computing? It's basically aggregating as much computing power in a way that you get better performance than you would if you had only one computer. So bit of history lessons. High performance computing is done, of course, on supercomputers, or they are world's fastest computers. Through history, it all started with vector supercomputers. The first one being, or one of the first one is Cray. Cray 1 from 1976. Its performance was 160 million floating point operations per second. Besides vector supercomputers, there were massively parallel computers, one of which is you probably heard of IBM's Blue Gene, and its performance was 360 teraflops, so big advance. And one other kind of high-performance computers is our computer clusters, and that is something that I'll talk about today because that's something we have at Srce. Well, what is this computer cluster? It's actually just a set of connected individual computers that function as a single computing resource. And I think this picture pretty much sums it up. It's sometimes called a poor man's supercomputer because it's extremely cheap compared to the vector supercomputers and massively parallel computers. What is common about every supercomputer of this type is parallelization. It means breaking down a problem, something you have to calculate, compute, into smaller pieces that can be run in parallel. And that is done traditionally on a huge number of processors or CPU cores. So today, supercomputers are ranked in a list called Top 100. It's a list of world's fastest supercomputer. It is updated 2 times a year. And their main performance criterion is something called HPL or high performance LinPack. In last few years, they have another benchmark. It's called high performance conjugate gradient. So there are actually 2 lists in top 500. Today, 85% of supercomputers on the list are actually computer clusters. And number 1 currently, since last year, I think, is Summit. It's located in Oak Ridge National Laboratory in USA. Its performance is 200 petaflops. So if you can compare it with the Cray 1, it's orders of magnitude larger. The Summit has over 2 million processor cores, but what is interesting for us and for today is that it has over 27,000 NVIDIA Tesla V100 GPUs. And that is the largest portion of its performance of the 200 petaflops. So in Zagreb, in Srce, in Isabella, we have a cluster that has 135 computing nodes which are connected together, making a total of 3,100 processor cores, total of 16 terabytes of RAM, storage, and we have 12 NVIDIA Tesla V100s compared to the 27,000. We got them last year, and since January this year, they are available for our users. Is anybody here a user of Isabella, maybe? No? Okay. No problem. So what are actually GPUs, just short? They were originally, of course, as their title is graphics processing units, they were designed to accelerate computer graphics. And because they are so specifically designed, They have a lot of cores, orders of thousands per GPU, because they accelerate, well, pixels individually. Yeah. So that enables such a large number of cores compared to a traditional CPU that has up to 30 cores today or something like that. Enables massive parallelism, which is of course ideal for problems that people calculate on supercomputers, which are basically mostly scientific nature. So today in top 500 there are 138 systems that use some form of accelerators. We call GPUs accelerators because they accelerate calculations on supercomputers. But there are, of course, other types of accelerators, specific chips, and so on. And of those 138, 123 use specifically NVIDIA GPUs. Because NVIDIA is really today one of the foremost producer of GPUs for high performance computing. Tesla V100 is the best GPU today, best server GPU available. It is based on the new Volta architecture by NVIDIA. It has over 5,000 cores. NVIDIA calls them Cuda cores. I'll talk something about it later. But it's the first GPU from NVIDIA that has something called tensor cores. Tensor cores are specific and they are very specialized for small dimensional matrix operations. And they are mostly used in machine learning workloads. Performance of one V100 is 7.8 teraflops, which is crazy. It comes in two variants, considering its memory, 16 and 32 gigabyte. In Srce, we have versions with 16 gigabytes. So in Isabella, they are implemented in 3 servers. They are Dell PowerEdge servers. Along with them, we have in every server 2 Intel processors. There are about 10 core processors, so altogether 20 CPU cores, and 4 Tesla V100 GPUs. Every server has 384 gigabyte RAM and 3.2 terabyte NVMe SSD storage. So it's basically everything is made so it's as fast as it can be, so it can keep up with the speed of the GPU. So as these are the first GPUs implemented in our cluster, previously we had some GPUs in Croatian National Grid infrastructure, but these are the first ones in Isabella. And when we got them, there were a lot of challenges implementing them in our existing infrastructures. First and foremost was implementing running GPU jobs with Isabella's job scheduler. On Isabella, we use Sun of Grid engine. The second problem is that we have a lot of users that use a bunch of different applications, and their jobs get assigned to a same compute node. So on one compute node, you have possibly 4 different users running 4 different jobs with 4 different applications. So that was obviously a problem. Of course, we wanted to keep the job submitting simple for users, because our users are not necessarily don't have IT background. They are scientists, they are chemists, they are biologists, and whatnot. So all the procedures had to be kept simple and consistent with what they were used to with submitting their jobs on traditional CPU processors. And of course, we wanted to maximize resource utilization, so we don't have GPUs sitting idly, or someone using only CPUs and GPUs doing nothing, or having a bunch of CPU cores that do nothing. And of course, we had to make sure that someone doesn't overuse resources on a compute node, say they use one GPU, but they occupy 20 CPU cores, so we have 3 GPUs that go wasted per compute node. So what did we do? Jobs in Isabella are submitted and they go into job queues. So we would ideally want that when a user submits their GPU job, that it goes in one single job queue, and when the job gets on top of the queue and GPU becomes available, it will go to its GPU. It will start running. Unfortunately, our version of grid of job scheduler doesn't recognize GPUs as a resource, so it cannot directly assign a job to a GPU and its corresponding CPU core that controls the process. So we had to figure out a way to go around it. What we did in the end was we had 12 separate queues, so each GPU card got its own queue. So when a job gets submitted, it just goes in one of the empty queues on one GPU. The next thing we had to work on was what if someone wants to use more than one GPU. So we have something called parallel environments. Not really important. So we have parallel environment called GPU that user submits and just says, okay, I want a GPU and I want this much GPUs. So if person says, I want 4 of them, the job scheduler will look, okay, how many queues are available. If there are 4 queues available, it will start a job on those 4 GPUs, and there can be sorted in any way. So you can have 1 GPU on one node, 3 GPUs on another node. Of course, because of the communication between nodes, that can cause some latency and drop of performance. So if someone has a program or application that doesn't necessarily can communicate between different nodes, we have another parallel environment called GPU single. So when you demand, let's say, 3 GPUs, and you specify parallel environment GPU single, all of your assigned GPUs will be on the same node, so your application will, of course, run faster. And the third parallel environment is GPU full. So maybe you want to use 4 GPUs and you want them all on one compute node, and maybe your job is also CPU intensive. This makes sure that you get all the 4 GPUs and all the 20 computer cores, CPU cores, and no other users are, I don't know, using a bunch of RAM, so you get an entire compute node. Since January, this is what we have observed, the statistics that 98% of users use only one GPU, and any more GPUs are under 1%, and I would say that everything above one GPU is me testing something on more GPUs. So, the reason why people use only one GPU, I would say, is because they are simply incredibly fast. Average job duration on Isabella is something around 24 hours, and we are talking about users who are used to having their jobs lasting for, I don't know, 3-4 days, sometimes a week. We have people running their jobs for a month. So when something lasts 24 hours, it's great for them. So why use more GPUs when one is enough? Which is great for us because we have more users can run their jobs faster. Second problem was the fact that we have more users per node and more applications per node. So we wrote some wrapper scripts that did the dirty work for us and for users. An example of that would be something like this. We called it Cuda Wrapper, let's say. So this wrapper does 2 things. This part assigns a job to correct the GPU. If anyone has worked with NVIDIA GPUs, Cuda visible devices in an environment variable that specifies which GPU the application can actually see. So if the Cuda visible device says only number 1, then the application can only physically, through the driver, see only GPU with ID number 1. So like that way, we work around the fact that our job scheduler doesn't recognize GPUs. And the first part is actually pinning the job to CPU controlling the GPU, because our compute nodes have this kind of topology. I don't know, it's pretty small picture, but basically you see that this first CPU is directly connected to all 4 GPUs, while the other CPU it's also connected, but it's not directly connected. So when a person wants a GPU, we make sure that the controlling CPU core is from this processor to, of course, maximize performance. Next thing was, of course, keeping job submitting simple for users. So for every type of job, like you saw a previous Cuda wrapper, we have specific special wrapper for them. So basically what the user does is they submit the job, GPU job, the same way they did with any kind of, let's say, normal traditional CPU jobs that they are used to. Basically it comes down to something like this. They say Cuda wrapper, and I know this is some kind of Python job or anything else. And they specify, I want 1 GPU. Cuda wrapper does everything for them. Next thing was maximizing and restricting resource utilization. The problem is that some applications only are GPU intensive, while others benefit from additional CPU cores. So that was a problem. So we made it possible for users to request additional CPU cores for their jobs using a special SG, our job scheduler attribute. What we did was that if a user requests additional CPU cores, they get a CPU core that is from the CPU on the right side from the previous picture. So there are actually a lot of applications that benefit from extra CPU cores. And this is the statistics. 12% of all jobs since January were using multiple CPU cores alongside with the GPU, 1 or more GPUs. And lately we've seen this number going up, so the percentage will probably over time get even bigger. Something about NVIDIA software available. We support Cuda version 9 and 10. 10 is the latest version of Cuda, but some applications like TensorFlow, for example, doesn't officially support Cuda 10, so Cuda 9 is also available. There is NVIDIA's deep learning network, deep learning library, CUDA, and NCCL, which is NVIDIA library for intercommunication between GPUs and between compute nodes. And for both versions of CUDA, 9 and 10, we have multiple MPI implementations, so because some applications work maybe only with OpenMPI or so. So users really have a lot of options, and their applications can run up as best as they can. As far as the GPU accelerated software goes, NVIDIA has their own CUDA programming language. It's something like C-like syntax. And today, most traditional high-performance computing scientific applications have a GPU accelerated version. So science software is keeping up with the advances in this field. Of course, something that, if you've heard of these GPUs, that NVIDIA is bragging about is that they are the best GPUs for artificial intelligence and machine learning workloads. So if you see an ad on the internet for NVIDIA, you'll probably see something about AI, TensorFlow, PyTorch. Everything that is run on Isabella and GPUs is almost exclusively open source, except for I think, one application for chemistry or something like that. Most run applications are these. Amber and Gromax are, I think, molecular dynamics and chemistry programs applications. After them are TensorFlow and PyTorch. I personally was expecting TensorFlow and PyTorch to be on the top, but they are lagging behind somewhat. But lately we've seen more and more users coming and using them for machine learning. There are some users that wrote their own proprietary Cuda code, a mathematician from Faculty of Science, and some other applications. As far as machine learning libraries that are available, we have TensorFlow, the newest version 1.12. I think it's still the newest major version before TensorFlow 2.0 comes out later this year, I think, and PyTorch version 1. They're both installed for Python 3.5 and Cuda 10. As I mentioned, TensorFlow doesn't officially support Cuda 10, but you can compile it from source. I tried and it works without a problem. As far as using multiple GPUs at the same time, that was a big problem while testing, because TensorFlow has a weird mechanic for using multiple GPUs. So we went with open source library called Horovod by Uber, and it's really easy to use. It requires only a few lines of code additional to your Python program to make sure that it runs on multi-GPUs, and it really easily works with our great job scheduler. So it worked well for us. We don't have, as I said, 98% of people use only one GPU, so we haven't had many people using multiple with Horovod, but I hope we will see more and more in the future. The problems currently with machine learning libraries are restricting CPU usage, because that responsibility lays exclusively on the user. So when someone writes their program, they have to make sure that they use that many CPU cores that they request. We had users that use one GPU and they use all 20 CPU cores, and that of course gets in the way of other users, because our job scheduler doesn't constrict your program to as many CPU cores as you requested, it only reserves them for you. So that was a problem. Second problem was that PyTorch jobs on multi-GPUs are not currently supported because of a bug in PyLint, I think with GNU-C compiler, and we will probably have to update the version of our GCC, and hopefully that will resolve it. What we plan to do in the future, of course, continue monitoring performance and adjust our infrastructure accordingly. Hopefully get more and more users, specifically, as I said, machine learning users, and of course resolve our bug with multi-GPU PyTorch jobs. Thank you for listening. If there are any questions?
Actually, I have two.
Okay.
So can you tell us how do you actually fit those V100 chips on the motherboard? They don't seem to be PCI Express.
No, they use, okay, to repeat the question for live stream, the question was how do we fit the GPUs on the motherboard because they are not PCI Express. No, they use NVMe version 2, NVLink, pardon, excuse me, NVIDIA NVLink 2.
Motherboard have to have this particular socket.
Yeah. So we didn't physically make the nodes, they came from Dell. So they made them. I didn't physically connect them. But yeah, they are not PCI Express. They are NVLink 2, which is much faster than PCI.
Okay. And one more.
Yeah.
So you mentioned that there is this share of applications where Amber is dominating, Gromax is the second one, and then there is like a minor usage of the deep learning software. So do you expect this to flip? I'm actually surprised about Gromax since they don't really support that well this GPU-only mode. They mostly support like GPU, CPU mode. So how do you expect this to flip over time? Do you have like interest in deep learning or?
Okay, so again, to repeat the question was about ratio of most run jobs on the GPUs. So basically, Gromax, you're right, doesn't it wants more aside from one GPU, it wants more CPU cores. And most people that run Gromax, I think most of them use one GPU and something like 10 CPU cores, which is still okay because Ember uses only GPU, so it takes only one CPU core. So they can run really well together. Users that use TensorFlow, we have one user that uses something like 8 CPU cores and like that, so it's still something that they can run all three of them together. As far as if I'm expecting these numbers to flip or the categories to move around, I don't think so in the near future, but we'll see. Ember, we have a lot of Ember users, and they stack their jobs, like they run 100 of them in the queue, and then they go away for 2 weeks. Gromax users, their jobs last something longer, and since it is not that much faster than CPUs, they just run like 10 of them on the GPUs and like 20 more on CPUs, and then they return in a week. So I think that's why Ember is leading, because it is much, much faster in its GPU version than it is in its CPU version. Any more questions? Yes?
The memory model, the memory is the same for all users and processes. So you don't share, you don't have NUMA.
Okay, the question is about the memory model, if it is shared between users. The RAM, server RAM, yeah, it's shared between all users. But what is common on Isabella, that most of these applications use very little RAM, so it's never really a problem. Okay, if that's it, thank you very much.